Welcome to the IPsec VPN Concepts module. This module explains how to identify various types of VPNs. It describes IPsec VPNs and their functionality. It also describes IPsec VPN establishment and IPsec traffic processing. At the end of this module, you will be able to identify various types of VPNs, describe IPsec VPNs and their functionality, describe how IPsec VPNs are established, describe IPsec traffic processing. VPNs are primarily used to transport private network traffic over a public network infrastructure. The term VPN has been used broadly in the networking industry for decades. For instance, the networking industry has referred to X.25, frame relay, and asynchronous transfer mode or ATM infrastructures as VPN networks. As the Internet grew and as carriers and service providers migrated all their service offerings to IP, new forms of VPNs emerged. These new forms of VPNs can be subdivided into 3 categories. Click each category to learn more. A network device that builds secure VPNs must be able to perform the following actions. Encrypt the original packet so that it cannot be easily decoded should it be intercepted on the public network. Verify the original payload, ensuring data integrity, and authenticate the originating device as a member of the VPN. 3 major security concerns exist for network security: integrity, source authentication, and confidentiality. Click each security concern to learn more. You must ensure that data is not subject to unauthorized modification. Even though a hacker might not be able to crack the encryption algorithm and key, they can still cause damage by modifying bits in the encrypted payload. Hashing solves this problem by creating a fingerprint of the data, similar to a cyclic redundancy check or CRC checksum. Before data travels, it is processed by a hashing engine using one of the various hashing algorithms available. This produces a fixed-length hash output that is placed in a field in the packet along with the data before it travels over the network. The destination device takes the same data and runs it through the same hashing algorithm, calculating its own hash. The destination device then compares the hash that it calculated against the hash sent in the packet. If the 2 hashes are identical, then this proves data integrity in transit. If the hashes do not match, the packet drops. The most widely used hash function is the Secure Hash Algorithm 1 or SHA-1. SHA-1 is preferred over Message Digest 5 or MD5. Though MD5 is still widely supported, it is no longer considered secure enough for many purposes. These functions produce a fixed-length output that is useful when working with IP packets because the overhead of transmitting the hash value is predictable. Junos OS supports MD5, SHA-1, and SHA-2 256-bit hash algorithms. A hash function must have 2 basic properties. It is a one-way function. In other words, you should not be able to calculate the original data from the hashed output. This property ensures that a third party cannot reverse the hash to obtain the original data or predictably produce the same output after modifying the data. It must be as collision-resistant as possible. A collision occurs when 2 different inputs give the same output. It must not be possible to predict a different input value that gives the same output. This property is necessary because the purpose of hashing is to verify that the data has not changed. To see how it is possible to create a one-way function, think of the example on the screen which shows a modulus operation. Given the output of 3, it is not possible to determine the original value because an infinite range of possible inputs exist. However, this example is not suitable as a real-world hash function because it does not satisfy the collision-resistant requirement. A malicious person can change the plain text by any multiple of the modulus number and know that the hashed value remains the same. The following list outlines the hash process. The sender runs the data through the hash algorithm, which creates a hash value. The sender appends the hash value to the data and sends both the data and the hash value to the receiver. The receiver separates the data and the hash value. The receiver hashes the data. The receiver then compares the calculated hash value to the received hash value. If the hash values match, the data is unaltered, providing data integrity. Hashing verifies that the data is unaltered. But how do you validate the source of the data? One method is to perform source authentication by using a hashed message authentication code, or HMAC. The sender appends a secret pre-shared key to the data, then performs the hash function. For hashes to successfully match, the receiver must append the same key value to the data before performing the hash function. The key itself never transmits along with the data. The following list outlines hashing with HMAC. The sender appends the pre-shared key to the data, then performs the hash function. The data and hash value travel to the receiver. The receiver separates the data and hash value. The receiver appends the pre-shared key to the data, then performs the hash function. The receiver compares the calculated hash value to the received hash value. If the hash values match, the data is unaltered, providing data integrity. If the hash values do not match, either the data itself is corrupt or the keys do not match, meaning the source is invalid. Either way, the receiver discards the packet. Juno security devices support the hash algorithms shown on the screen. Encryption provides data confidentiality. Encryption is the method of taking user data, referred to as plain text, and converting it into unreadable or secret data named ciphertext. An encryption algorithm and keys, which are strings of bits that seed the encryption process, are applied to the data, resulting in ciphertext. To reverse the process and decrypt the ciphertext, you must know both the encryption algorithm and encryption key or keys. There are two basic encryption paradigms. Symmetric key encryption. This method uses the same key for both encryption and decryption, and asymmetric key encryption. This method uses a key pair, consisting of two keys that are mathematically related. Either key can be used to encrypt, but the remaining key must be used to decrypt. The two keys in the key pair are referred to as a public and private key. The cipher strength depends mostly on the key size. The larger the key, the more secure the cipher output. The trade-off is in processing time. Larger keys use more computational cycles to encrypt and decrypt. Symmetric key encryption is the most straightforward form of encryption with the least amount of overhead. We refer to it as symmetric because the key used to encrypt the data is the same key used to decrypt the data. Thus, the same key must be known on both sides of a connection. Symmetric key sizes range from 56 bits to 256 bits. These keys are considered to be very fast because they are not very long, and they are widely used for bulk data encryption. However, because the key must be known to both the sender and the receiver, key management is a problem when using symmetric keys. Examples of symmetric key encryption include Rivest Cipher 4 or RC4, Data Encryption Standard or DES, Advanced Encryption Standard or AES, and Blowfish. Here are the Juno security devices that support the symmetric encryption algorithms. Suite B is a set of unclassified cryptographic algorithms initially released by the National Security Agency, or NSA, in 2005 to encourage industry investment in commercial communication security technology. NSA created Suite B as part of its cryptographic modernization program, while preserving its unpublished Suite A algorithms, which are employed to protect the most sensitive communications and authentication systems. Although it is designed to meet the rigorous protection requirements for national security information processing, Suite B cryptography also has tremendous value for organizations beyond law enforcement, intelligence, and Department of Defense or DoD communities. Other public sector agencies, as well as security-conscious commercial concerns, may choose Suite B to protect data stores of financial data, health data, intellectual property, and other private information. Suite B makes use of layered encryption that enables vendor-neutral integration for diverse devices. Suite B is available for Junos security devices running Junos 12.1x45 and above. Junos 15.1x49D40 or higher is needed on the VSRX. It is fully supported on SRX 5600 and SRX 5400 devices. If you configure IKE with Suite B options on these devices, you should ensure you have hardware-accelerated processors to ensure that VPN establishment happens quickly. Suite B makes use of the most secure algorithms for encryption and hashing, such as the AES-128 or AES-256 and SHA-2, SHA-256, or SHA-384. Elliptic curve cryptography, or ECC, was introduced as an alternative to RSA in public key cryptography. One advantage of ECC over RSA is key size versus strength. For example, a security strength of 80 bits can be achieved through an ECC key size of 160 bits, whereas RSA requires a key size of 1024 bits. With a 112-bit strength, the ECC key size is 224 bits, and the RSA key size is 2048 bits. The most popular signature scheme that uses elliptic curves is the Elliptic Curve Digital Signature Algorithm, or ECDSA. The most popular key agreement scheme is Elliptic Curve Diffie-Hellman, or ECDH. An ECDH exchange is a variant of the Diffie-Hellman or DH protocol, and both ECDH and ECDSA are integral parts of the Suite B cryptography. If a device supports Suite B, then the algorithms are added to the following configuration options. Click each configuration option to learn more. Asymmetric encryption requires a pair of mathematically related keys. Either key in the key pair can be used to encrypt, but the remaining key of the key pair must be used to decrypt. In practice, one of the keys is kept secret and known only to the owner. This key is the private key. The owner distributes the other key of the pair widely, and anyone can access it. This key is the public key. You can only decrypt data encrypted by the private key by using the corresponding public key and vice versa. The keys are mathematically related, such that it is almost impossible to derive one key out of another. Public key sizes range from 512 to 2048 bits. Because of the large size, these keys are extremely slow and generally not feasible for bulk data encryption. However, public keys are widely used for user and device authentication, for example, digital certificates, and can be used to compute symmetric keys to address the problem of secure key distribution. Examples of asymmetric encryption include DH and RSA. An encryption function is a two-way function that can use modulus functions but operate in a different way than hashing. The example shows that performing the first calculation is easy because all the variables are known except the final output. In the second calculation, you know the answer is 12, but don't know the exponent value. You would have to resort to trial and error to find matching exponents that give the correct output of 12. This can be easy with small numbers, but with large prime numbers, this becomes very difficult. Algorithms like RSA and DH both use this functionality, and the strength of these functions is based on the time needed to reverse. Using large prime numbers makes reversing the process impractical and could take years even with the computational power of some of the largest supercomputers on Earth. Both encryption and authentication are dependent on keys, which leads to the problem of key exchange. If keys must be the same on both sides of a connection, how can you securely exchange key information? One option is to manually configure the keys on both sides of the connection. Manual key configuration is straightforward, but misconfigurations are common, especially when each device has a different administrator. Manual configuration also usually means that keys rarely change, which is itself a potential security issue. Given a large enough time, these keys can be broken. Automating the key exchange process is a good idea, but you must overcome the problem of sending keys across a public network. Whitfield Diffie and Martin Hellman developed a solution to this problem in 1970. The DH algorithm is a method whereby two parties can agree upon a secret key known only to them. The strength of the technique is that it enables the participants to create the secret value over an unsecured medium without exchanging the secret value itself. This method also makes it computationally infeasible to perform reverse generation of the secret if it is somehow intercepted. Using the same DH group, each device creates unique public and private keys. The public key values exchange across the network. Each peer then computes a common session key using its local private key and the received public key through the DH algorithm. The session key itself never passes across the network. In this example, device A and B agree on a prime modulus of 17 and a generator of 3. Each then picks a random prime number and generates a public key which they send to one another. A uses 15 and B uses 13 as their respective private keys. A's public key is calculated as 3 power 15 mod 17 equals 6. B's public key is calculated as 3 power 13 mod 17 equals 12. They each then use a combination of their private key and their peer's public key to arrive at the same answer or shared secret. A calculates 12 power 15 mod 17 equals 10. B calculates 6 power 13 mod 17 equals 10. If you break down each side's calculation, you can see the functions are congruent, and that is where the magic happens. A. 3 power 13 mod 17 whole power 15 mod 17 equals 3 power 13 into 15 mod 17. B. 3 power 15 mod 17 whole power 13 mod 17 equals 3 power 15 into 13 mod 17. DH groups are sets of very large prime numbers which serve as the modulus in the key exchange process. Larger primes result in encryption that is harder to crack due to the increased computing time required. However, larger primes also result in slower encryption speeds. Juno security devices currently support the DH groups displayed on the screen. IPsec is a set of standards that defines how the encryption, validation, and authentication methods are actually implemented in networks. IPsec works at Layer 3 and supports both unicast and multicast traffic. IPsec provides the integrity, source authentication, and confidentiality needed for data transiting an insecure medium such as the public Internet. With IPsec VPNs, the IKE protocol is typically used to set up a tunnel. IKE works in two phases to set up the tunnel. The first phase, also known as the IKE phase, sets up a secure channel used to negotiate how traffic will be secured for the second phase. Once negotiations are complete in Phase 1, then a second tunnel is established in Phase 2, also known as the IPsec phase. After Phase 2 is complete, the data traffic can now securely traverse the IPsec VPN tunnel. IKE is a secure key management protocol used by IPsec to exchange information in a secure and dynamic manner with little or no intervention. The IKE proposal exchange is part of the IPsec tunnel establishment process. The attributes that exchange between IPsec peers as part of the IKE process are encryption algorithm, hash algorithm, authentication method, and DH group. Once IPsec peers negotiate these attributes, they secure future attribute exchanges used to protect data. IKE exchanges authenticate using one of the following methods: pre-shared keys, digital. A security association, or SA, is a set of policies and keys used to protect information. SAs establish upon the successful completion of IKE negotiations. An SA is uniquely identified by the Security Parameter Index, or SPI value, the tunnel destination address, and the security protocol, encapsulating security payload, or ESP, or authentication header, or AH. The lifetime of an SA can be based on either a time value or a quantity of bandwidth, after which the keys are changed, a process known as rekeying. SAs are stored in a security association database. Each entry includes the name of the particular VPN, the remote gateway IP address, the SPIs for each direction, the agreed-upon security protocol, encryption, and authentication algorithms and keys. The SA database is an important mechanism to keep track of all the SAs installed on the Juno security device. Each packet that comes over a VPN tunnel has the SPI included in the packet header that is used to look up the corresponding SA in the database to correctly handle the packet. The packet headers will be discussed in more detail later in this module. IKE tunnel establishment happens in two phases. Phase 1 establishes a secure channel between gateways for Phase 2 negotiations to occur. The DH key exchange algorithm establishes a shared secret that is used to derive the encryption and authentication keys. Phase 1 uses a pre-shared key or a digital certificate for peer endpoint identification or PEI or authentication. Remember, public key cryptography algorithms are more secure but are also slow and more resource-intensive. Due to this, a single Phase 1 channel can establish multiple Phase 2 SAs or VPNs between the same peers, so rekeying happens less frequently by default. IKE Phase 1 can be configured to operate in two modes. Main mode is used when both peers use statistically assigned addresses. Aggressive mode is used when one peer has a dynamically assigned address. In aggressive mode, the peer with the dynamic address must initiate the tunnel. IKE main mode is used in Phase 1 when both tunnel peers have static IP addresses. At a high level, each exchange of messages is used for the following purposes. The first two messages validate the peer configuration by checking the cookie against the locally configured peer IP address and negotiate the SA parameters. Both tunnel peers must have at least one configured matching proposal for Phase 1 exchange success. The next two messages exchange DH public key values and nonces necessary to compute the shared key. The last two messages send simple identification information using the negotiated key. These messages validate that the key calculation is correct. In Message 1 and Message 2, peers exchange cookies and SA proposals. Cookies are 8-byte pseudo-random numbers generated by the sending machine, or I equals initiator, and receiving machine, or R equals responder. Every cookie is unique to the machine and to each particular exchange. These cookies guarantee uniqueness and replay protection by hashing the sender's IP address, port, protocol, and timestamp, which results in a unique identifier known only to the originator. Hence, they are included in every IPsec packet and used to identify communication. In turn, the receptor inserts its known cookie in Message 2 if it accepts the SA proposal. The IKE SA proposal contains the Phase 1 authentication method, either main mode or aggressive mode, DH group number, encryption algorithm, authentication algorithm, and key lifetime. In Message 3 and Message 4, the DH public values exchange to create a common session key. Nonces, which are essentially random numbers, also exchange at this time for use as seeds for keys generated later. After both sides exchange their DH public values, a shared secret key is created on each side, which is used to derive all other keys, including the encryption key for the rest of the IKE Phase 1 messages. In Message 5 and Message 6, the peers send simple identification information using the negotiated key. These messages validate that the key calculation is correct and use the pre-shared key in the HMAC algorithm. IKE aggressive mode is used when one of the tunnel peers has a dynamically assigned IP address. Examples include a remote end user dialing into the Internet or a remote site using Dynamic Host Configuration Protocol, or DHCP, to acquire an IP address. Main mode cannot be used in this situation because the first two messages validate peer IP addresses, and the dynamic host address cannot be pre-configured on the peer device. Phase 1 aggressive mode must be initiated by the device with the dynamic IP address. The first two messages negotiate SA proposals and exchange DH public values, cookies, and nonces. In addition, the second message authenticates the responder. The ID hash is compared with a locally configured peer ID. The third message authenticates the initiator and provides a proof of participation in the exchange. Phase 2 establishes the VPN connections. SAs for Phase 2 are to determine the encryption and authentication algorithms to use when sending user data. The SA is identified by a unique SPI that is also negotiated during Phase 2. Optionally, a second DH exchange can be performed during Phase 2 to negotiate a new tunnel key. This is also known as Perfect Forward Secrecy, or PFS. Phase 2 can take advantage of values calculated during Phase 1 to avoid repeating the work required to generate keys. The default rekey lifetime for Phase 2 is 1 hour. Phase 2 uses proxy IDs to identify the VPN peer. Proxy ID creation occurs at the very beginning of the Phase 2 negotiations. Proxy IDs are discussed in more detail later in this module. Once Phase 1 is complete, proposals exchange to establish a Phase 2 tunnel used for a specific VPN. Upon successful completion of quick mode, user data encrypts between the configured IPsec peers. Both tunnel peers must have at least one matching proposal configured for Phase 2 exchange success. The result of Phase 2 is to create an IPsec VPN for user data to securely transmit through the network. In messages 1 and 2, a Phase 2 SA proposal list exchanges. The list contains encrypted and authenticated information that determines the algorithms and keys for encrypting and authenticating user data. The Phase 2 proposal list contains the following items: security protocol, encapsulating security payload or authentication header, or ESP-AH, DH group number, 0 for no PFS, DH public keys, optional if using PFS, encryption algorithm, authentication algorithm, key lifetime, and proxy ID policy rule. Message 3 acknowledges information sent from quick mode message 2 so that the Phase 2 tunnel can establish. IKE defines the specific method and messages used to negotiate VPN tunnels. The configuration of either version is exactly the same with the exception of configuring the IKE version to IKE-v1 or IKE-v2 only. If you choose not to configure an IKE version, the default version is IKE-v1 only. IKE-v2 uses 4 exchanges for negotiation and does not have 2 technical phases like IKE-v1. The IKE-v2 Child Security Association is known as a Phase 2 Security Association in IKE-v1. These message exchanges are discussed in more detail later in the module. Support for IKE-v2 was added as of Junos 11.3R1. Like IKE-v1, IKE-v2 creates 2 sets of SAs. The first set of exchanges are known as IKE-SA init and work similarly to Phase 1. The first message from the initiator to the responder contains the SA proposals, DH keys, and nonces. The second message from the responder to the initiator contains the same set of information. The peers can generate the shared secret key used to derive the keys used in the IKE-SA. All future messages will now be protected by the encryption and authentication methods selected in the process. The second set of exchanges is known as IKE-Auth. In messages 3 and 4, the initiator and responder exchange identity information used for authentication. Once the identity of the peer has been validated, the first child SA is created, which is the equivalent of the IKE-v1 Phase 2 IPsec SA. The illustration provides a summary of all the steps of IPsec traffic processing. During the IPsec traffic processing step, the devices have one goal: to ensure traffic protection. The most commonly used IPsec mode is ESP tunnel mode using a route-based VPN. IPsec uses two protocols to ensure payload security: the AH protocol and the ESP protocol. Both authenticate peers and verify data integrity, whereas ESP is the only one that encrypts the data payload. Each of these protocols are discussed later in the module. IPsec handles the payload using one of two modes: transport mode or tunnel mode. Transport mode is generally used for remote access VPNs, where the end-user devices are creating the VPN. Tunnel mode is used for site-to-site VPNs, where the gateway devices are creating the VPN. We discuss each mode later in the chapter. Two protocols exist that IPsec can use to ensure payload security: AH and ESP. AH provides data integrity, authentication, and anti-replay services. AH is identified by IP protocol number 51. It uses MD5 or SHA-1 to provide data integrity services. However, AH provides no encryption of data in the packets. ESP provides data confidentiality in addition to data integrity, authentication, and anti-replay services. ESP is identified by IP protocol number 50. It uses symmetric key algorithms like DES, 3DES, or AES, and hash methods like MD5 and SHA-1 to provide security services. Neither AH or ESP use a transport protocol like TCP or UDP. They ride directly on top of IP using their respective protocol number. Anti-replay services ensure that third parties cannot capture and retransmit datagrams. By checking sequence numbers, a receiver can determine receipt of a packet and can discard any repetitions. You can implement IPsec in the following two modes. The transport mode is implemented between IPsec end systems. End systems should be aware of the IPsec protocol suite and perform all of the encryption and decryption of data. The tunnel mode is the most commonly implemented method. Tunnel mode is implemented between IPsec gateways or an IPsec gateway and a remote client, thus providing secure access to the networks behind the gateway. In this method, end systems do not need to be aware of the IPsec protocol suite. All encryption and decryption take place on the IPsec gateways on behalf of the hosts behind the gateway. There is no explicit way to set the mode. What distinguishes transport mode from tunnel mode is the next header field in the AH or ESP header. If the value is IP, it means that the packet encapsulated an entire IP datagram, so it uses tunnel mode to secure connection between two gateway devices. If there is any other value such as TCP, UDP, or Internet Control Message Protocol or ICMP, there is no outer IP header, so it uses transport mode to secure an endpoint-to-endpoint connection. With AH, the mode can be determined easily by an onlooker, but with ESP, the information is part of the encrypted payload and not visible to anyone unable to decrypt the packet. In tunnel mode, AH authenticates only the immutable fields in the IP header. Fields like time to live or TTL and type of service or TOS change during packet transit, so these fields do not receive authentication. The new IP header contains protocol number 51, signifying AH. The AH header contains the following items: next header, payload length, SPI, sequence number, and integrity check value or ICV. Click each item to learn more. In tunnel mode, the ESP header inserts between the new IP header and the original IP header. The new IP header contains protocol 50, representing ESP. The ESP header contains SPI and sequence number. The ESP trailer contains padding or pad length, next header, and ICV. Click each item to learn more. In this example, two Juniper security devices have already been configured to use route-based IPsec VPNs. The traffic processing sequence for a packet attempting to traverse the IPsec VPN tunnel is displayed. Here are the steps, starting from the device in the remote office. The packet arrives at the remote Juno security device on interface GE0/0/1. The Juno's OS looks up the destination route, which resolves in the ST0.0 interface as the egress. This allows the software to determine the egress zone as well. The Juno's OS looks up the security policy for this zone context. The traffic matches a permit policy. The original packet receives encryption. The Juno's OS hashes the packet with an authentication key. The Juno's OS builds the tunnel packet with a new IP header, IPsec header, and hash value. The new packet travels to the tunnel peer. The list is a continuation of the list from the previous screen describing the order of traffic processing. The corporate Juno security device receives the encrypted packet. The Juno's OS looks up the incoming SPI in the local SA database. The matching record contains encryption and authentication algorithms and keys. The Juno's OS compares the locally calculated hash with the received hash. The Juno's OS decrypts the packet. The Juno's OS performs the routing lookup for the decrypted packet and determines the egress zone. The Juno's OS checks the associated security policy. It forwards the packet if a permit policy exists for the packet. You have reached the end of this module. In this module, you learned to identify various types of VPNs, describe IPsec VPNs and their functionality, describe how IPsec VPNs are established, describe IPsec traffic processing. For additional Juniper training and information, we recommend the following: Juniper Networks Learning Paths, Juniper All Access Training Paths, Juniper Learning Bites, Juno's Genius, Juniper Networks Certification Program or JNCP, Juniper On-Demand Training, Juniper Networks Books, JNet Training Certification and Career Forum, Day 1 Books. Click each label to learn more. Lastly, be sure to follow us on Twitter at Juniper Certify. Congratulations! You have reached the end of the Introduction to Juno's Security course.